Hello, everyone. Let's start with our next topic. It's called Remotely Snooping on Traffic Patterns Using Network Protocols by Kirils. Enjoy it.
Thank you. So let's hack some networks. And before I start, I'd like to extend my sincere thanks to my colleague, Petris, for helping me test much of this stuff that I'm going to talk about today. And well, before we get into that, a little bit about me, for those of you who don't know who I am. Should have tested this on the big screen. It can't. It froze. Nice. Okay. Well, in hopes that I will not have to reboot my computer and it will just magically advance to the next slide at some point. So, my name is Kirils. By day, I run a small security company of about 10, 11 people called Possible Security, but I do yearn for the days when I could hack and spend 7 days of the week doing fun stuff. One of my areas of expertise is network flow analysis, which is a bit tied in. Oh, perfect. So I have a movement here on this screen. A bit tied into what's happening here. Okay, now it should be working. As soon as the video guy is back. Ah, there we go. Right. So that's me in the suit. That's how I do my CEOing of the company. Right. So, as I was saying, network flow analysis, that's, I started it maybe like 20, 25 years ago. Then I went into reverse engineering, lots of fun. Can't really convert that into a business unless you deal with NSA and people like that, or criminals. Social engineering is fun as well. I do love to help with that. And penetration testing, of course, as many of us here are interested in that, of course, as well. Some of you may be participating in CTF. I hear it's quite a fun one. I haven't had the time to participate yet since I was doing the animations for the presentation for the whole day. You can follow me at chaos.social. That's my English-speaking account. I tweet, and I use this word intentionally. I tweet over there fun stuff about IT security. Okay. So this is what we can talk about, and I structured the presentation in such a way that you can come with me on a journey on how I was developing and how I keep developing the tooling for this quite innovative research, as far as I can tell. So we're going to go step by step. But before we go into that, let's talk a bit about network theory, and let's start with networks. As we are all aware, internet is akin to a series of tubes. Really a lot of similarities there lately, with everything turning to poo. Do you know the author of the quote, by the way? Well, it's actually US Senator Ted Stevens, not a particularly witted individual, and not a fan of net neutrality. So let's get on to some theory. Oops. There we go. Now I see the slides as well. So there are three terms that we're going to be dealing with for the whole presentation: bandwidth, throughput, and latency. The first two are really. How many of you could explain like what's the difference between bandwidth and latency? Anyone? 1, 2, 3. Okay, 4. Probably network admins. It seems intuitive at first, but when you start thinking about it, you really have to think about it. So bandwidth is basically the potential to transfer data. How much space you have, how wide is the tube, right? And throughput is what's traveling right now through the pipe, right? How much poo is going through there, right? And then latency is how long until the first drop travels through, or any drop travels through the pipe, right? So we have a single droplet of, let's say, Nyan cat meme, and it's traveling through the pipe. So latency is the time in milliseconds or seconds, whatever, how long will it take from point A to point B. And what we're exploiting here in this research is this. So latency is directly correlated to throughput over bandwidth. The less free bandwidth you have, free bandwidth is the remaining bandwidth after your stuff is flowing through the tube, right? The less free bandwidth you have, the higher the latency. And we can, of course, measure the latency remotely. We have tools for that, like Ping, for example. By the way, I spent like 1.5 months trying to move away from Ping into something more sophisticated. I had plans to use maybe SCTP to take a look at the TCP SYN packets. You'll see how that went. Right. So this is the network layout. In the middle, the 4 nodes there, that's the internet, right? Internet doesn't have a center, of course, but for any 2 endpoints, there is like the middle somewhere, where all the wide pipes are. And please take note. It's intentional that some of the pipes are wider than the others, visually. That represents the available bandwidth of the pipe. And this is the usual configuration, where Alice does not have a pipe as wide as the backbone up on top, right? So here we have a network, Alice's network, that has a laptop and a TV locally, and Alice, the node that's named Alice, is the router, the home router of the target network, which connects to the ISP router. It's a bit simplified diagram here. And we have Mallory, which is us, that also has not too wide of a pipe, and we're trying to do something here. So methodology that we're going to use here. Basically, easy, right? We're Mallory, we ping 2 nodes, and it's super important to ping them at the same time. So we have to put the pings out in the same millisecond. Even higher precision is of course even better. So we determine the IP address of the home router. We determine the previous hop that is outside that network, which is one network up on the ISP, and then we ping them both at the same time. And then we get a pong from one of them. Usually the first pong will come from this device here, because it's closer to us, and because the pipes are wider. The minimum pipe width is well, the minimum bandwidth is higher, right? And then sometime later, a second pong will come from Alice's router, right? And all we do is we calculate the delta between the second pong and the first pong. That's it, the time delta, right? Time difference between them. For verifying the research, we also install a NetFlow collector right here to compare the data that we're getting to the actual data that is available at the network that we are attacking. So basically, that's it. That's the theory, and I'm gonna continue talking much about tooling and also a bit about results, or rather, much about results, a bit about tooling. Yeah, I guess that way. Before that, I have a quick quiz for the audience members right here, for the esteemed experts in the audience. So that's a question here. So anyone who's an expert in GNU core utils or command line, what does tr equals empty string means in this command? Anyone? I'll buy you a drink later tonight at the party. Yeah, everything. Okay, then you buy me a drink. I'll tell you. So it's a trick question actually. So what's happening on the line that you see on the command line that you see on the screen? We are actually executing a program called stdbuff, which modifies the behavior of input, output, and other buffers of a different command. So what's happening here? We are running command tr, translate, which simply replaces all the equal signs with a space. And before we do that, we modify how the buffers behave. So basically, we're setting input buffer length to 0, output buffer length to 0, and error buffer length to 0, thus turning the buffers off, turning off buffering, and getting the data faster without it being stuck in the buffer, right? So, why the question? Well, because the tooling prototype that I wrote in April was, of course, written in Bash, or rather, it wasn't even Bash, it was more like command line terminal, right? So 2 simple commands. We run command number 1, command number 2, and everything's happening, right? So we have a target, we have uplink, and we ping them both using a packet size in this example of 10K. of course, we want to get the data out in a timely manner, so we use unbuffer. Unbuffer is just an alias for the abomination you saw on the previous slide, which is much easier to read, I believe, right? And cell call is a small script that's AWK, basically. I just really dislike typing curly brackets. I never learned Dvorak, so I use QWERTY, and it's a pain to type curly brackets, so I wrote cell call, which basically is AWK print $6, print $10 in this example here. Right, so that's basically what's happening, and then we teeing it all into a file, test target and test get, and then we can compare it later on. Any problem here? Would this work?
Probably not consistently.
Why? Why wouldn't it work consistently?
Because it's not sending at the exact same time.
Yes, because it's not sending the packets at the exact same time. So since I'm stuck with Bash. By the way, I moved into Bash after PHP, so everyone was kink shaming me about my love for PHP 3, and then I started doing Bash. So that now that's my golden hammer. That is why the answer is always Bash. And of course, this is how we do it. This is how we synchronize two different terminals doing the same stuff. So we choose a start time sometime in the future, let's say 5 seconds or 20 seconds in the future, and we write this nice while loop in Bash and some sleeps and done, and basically we prepend it before the ping command. So the loop loops, and then the date comes, and then we have it running at the same time afterwards. Really easy, right? So we have two synced ping commands there. And so those are 4 lines. And one more line, just visualize it. So basically we use paste. Paste is like, if you don't have Excel or LibreOffice Calc, you can use paste to just add columns, add 2 files side by side, add them as columns, right? And then we just subtract, two of the infos are there, and we chart them, we plot them. Once again, that's another script that I have because, true story, I was doing a master thesis in physics a couple years ago, and I didn't want to re-plot all 100 graphs that I had in my thesis every time I got new data, so I wanted to automate it using Bash, so I wrote a tool, command line tool that creates quite nice graphs, I believe. So, okay, this was a prototype in April 2024, so five months ago. And this is literally the first test of the prototype. So the first result. And it works, right? So this approach I also tested back in April against layer 1 bandwidth shaping and traffic shaping, layer 1 bandwidth limitations and traffic shaping as well. And here, someone on Alice's network which has 100 base TX physical connection up to the next hop or other next device is downloading a 1 gigabyte file unshaped, right? And we can see when the download begins, we can see when the download ends really clearly. And specifically those spikes on the end, that's what gave me the feeling that it's not just a fluke, that we will be able to actually get something out of it, because it's so the borders are really, really visible. Really, you can see them really good. So afterwards, after running the test, I was playing around with some more data, but I had also a bunch of work to do. As you can see, it was like almost 9 p.m. Where I was at the time when this test was run, and I went on to doing some more work stuff, and I accidentally left the test running overnight. I did apologize to my colleague afterwards, but he did confirm that the data matched. So basically, the spikes here are actual stuff happening. So there's you can see you can see the sleep time, right? So my colleague apparently sleeps somewhere between 3 a.m. and 8 a.m. So 5 hours of sleep. That's good. We can see some file uploads, I believe, over here. No, that's the downloads. This is the upload here, and we can see some video streaming here from 2 a.m. Really nice. I also watch YouTube when I get to sleep. So then June came, and I wanted to actually go from the draft prototype to a real tool set, right? I wanted to write a tool set for this research that I'm doing. So I thought I'm gonna write a tool set. So I sat down on my computer, I opened up my favorite text editor, Pico, or Nano, Pico, depends on your age. And I started writing. I wrote import asyncio, I wrote from concurrent features, import thread pool executor. They had no idea what I was doing. From Scapy, all import IP, SMP, SR1. This one I know. I've been using Scapy way before I learned how to use Python. And then I imported some time, of course. I imported datetime. And I wrote a code which made sense. It wasn't 5 lines anymore. It was a lot of lines, and it kind of did everything that my terminal stuff did. It didn't work. 58 lines doesn't work. Like no correlation, just random data coming out. Yes, you get deltas. They kind of make sense. They're mostly positive, but you cannot see. It doesn't correlate to anything that's happening in the network. I still don't know why. I told this at a conference 2 weeks ago, and someone said, "Hey, give me the Python code. I'm going to fix it." Never heard from him again. Do you want to fix the code?
Probably not, but it's very likely the global interpreter lock in Python that's messing you up.
Global interpreter lock in Python.
Because you cannot run multi-threaded things in Python. It needs to be multi-process.
I have the same problem.
Okay, people in the audience are saying they have the same problems. Yes.
I know how to fix it.
And there's an expert that knows how to fix it. I'll send you the code, or we can do it over a beer later on.
But not in Python, but I wrote an article about it.
Oh, cool.
How to measure latency while sending, receiving.
Oh, very nice, very nice. Okay, right. So, but my Python skills are average, medium level skills. So, I tried to get it to work in June and July, and finally in August 2024, I got it to work. In August 2024, there's correlation between what's happening in the network and the actual data coming out of the tool. It also determines the IP of ISP's router automatically. Currently, it takes like 30 to 40 seconds to do that, which is annoying, but I haven't re-implemented that because it works really well, other than the delay. It also supports multiple payload sizes. So instead of just measuring with, let's say, 10 kilobytes, you can measure with different payloads at the same time. The problem is that it can get desynchronized quickly. So it's good for running the test for like maybe 5 minutes, if you're lucky 30 minutes or 60 minutes, but if you run it overnight or multiple days, it will get desynchronized and your data will turn to what the internet is. I wrote in Bash. It was 3 files, 71 lines total, and it worked, which is really nice. Next month, this month in September, I improved upon the work. Now it resynchronizes every tick, which means it does not get desynchronized. You can run it like for a month if you want to. And it's not limited to 1 packet per second anymore. So let's say you're downloading a file that, your target Alice is downloading a file that downloads in half a second. You're not going to miss it anymore because it's not limited to 1 packet per second. And then I started, thinking, like, what will I trigger any defenses of ISPs on that end or that end, and how fast should I be sending 10 kilobyte packets of ping over the internet? Because I remember back in the days of the IRC, that was a thing you could use if someone was being bad on IRC to disconnect them from the server. So I thought about that, and nothing bad happened. No one got banned or disconnected. So it seems that in these days, when connections are 100 megabits a gigabit, it doesn't really matter that you're doing that. It's 75 lines in Bash. I think it was 1 file now, right? So now the tooling was done. Tooling was good. It was working. It was stable, and everything was nice. So now that the question is, right, why did I write a tool that is able to send multiple packet sizes? Because I do have the concern of sending large packets fast. You don't want to spam the network. It's not a good thing to do. I have been network administrator myself. No one likes that in the profession. So I have to make a decision. What is the correct packet size? Which is the most optimal packet size to send if I want to get the highest quality of data? So I did some measurements. This is measuring an idle network and sending all the packet sizes simultaneously. So as you can see, there is no correlation, right? It's like everything is trash, And not only is it's trash, but also these are milliseconds. So basically, we have stuff happening at about plus or minus 0.1 seconds, which is terrible for what we want to do, what we want to measure. So I once again spent like a week trying to interpret the data and then trying to improve the tool, and finally I came up with the current version of tooling, which is written in Bash. It sends packets one by one, which makes sense if you think about it. But you know, I have a lot of CEOing to do in my daily life, so I do this stuff at night after a beer or two. So I don't think that well. But if you think about it still, during daytime, you understand that if you send like 5 packets of different sizes at the same tick, then you're gonna measure like the whole thing, all the impact of all the 5 packets at once, which is why you don't see anything, right? So the fix was really simple. You just send packets one by one, and data is actually useful again. I had to remove some lines, add some lines, really small diff there. Now, this allowed me to come back to the question, what is the best packet size? Once again, this is idle network, but we are not sending different packet sizes at the same time. And we start to see some really useful data. Now, for it to be seen a bit better, we have to filter it out. So we filter out all negative values, which is usually due to packet being stuck somewhere. It's a packet switch network, so that may happen. And also network jitter is being filtered out. Since we are sending multiple sizes, it's really easy to find network jitter. First of all, it may be a peak, a large peak. We can filter those out, but also usually only one packet size will jump, and the other packet sizes will stay the same because it's random, right? So you can still see some peaks here, but you also see that multiple tests, multiple packet sizes running almost at the same time, not concurrently, but almost at the same time, gave the peak. So network was not fully idle, but mostly idle. And I was really happy to put those trend lines on there. I didn't request the plot to be horizontal. It is horizontal, which is really cool. It's just, it would have been tilted, but it is horizontal because the data is stable. And we can actually see the difference between different packet sizes and the average latency of the test. Another thing that we have to take a look at here is the stability. So it's also called jitter, right? The smallest jitter that we have is for packet size of 50 bytes. Maybe we can go even smaller, right? Because when I was doing this part of the research, I was kind of looking at the high end of the sizes, and I was thinking, okay, so how high should I go? I wasn't thinking how low should I go. So in my next iteration, I'm probably going to do 50 bytes and under, so 40, 30. Let's take a look at in that direction. But this is also useful, and this can be used for estimating bandwidth remotely. I actually validated this this morning. I had an idea that it should work, and I took out my diploma in physics, and I wrote a formula. So, by the way, fun fact: when I was writing my thesis in physics, I was really afraid that the people responsible for granting or denying me a degree would say that it's just an IT project, because my previous master was in computing, and I was doing my master's in physics, and it was like a lot of coding and not much physics. And then I was doing about building management or large management, building heat management, right? So I was exploring a theorem where sun was shining through the window, and I wanted to calculate how much cooling power would be saved if instead of using AC we would install blinds on the window. And I just wrote a formula slowly, and I got a double integral, and it was like a whole page, and I was so fucking happy, because there was one guy when I was doing my dissertation, and he asked, well, where's the physics? And I said, that page, there's the formula. So we also have a formula here. Basically what's happening here is we take the largest and the smallest packet of our test, right? Well, we average them first, right? These are here. In this example, that's 16K and 50, largest and smallest. We take the size of the packet. We add the overhead produced by header. So we have IP header, which is 20 bytes. We have ICMP header without the payload, which is 8 bytes. We add 28 bytes. And then we subtract them. and I mean, it comes down to this, right? And then we divide it by the deltas that we get. The average delta that we get from sending the large packet and receiving it back, and the small packet, right? And we multiply it by 2 because the packet is going both ways. So we're actually using up the bandwidth there, and then when it's coming back. So that's the formula. And I put in the numbers from the previous graph. And remember, the network we're testing is a 100 megabit network, right? So the inaccuracy is less than 0.05, which is really good. And you know, I got to think. So when I validated this morning, I got to thinking maybe it can be used to estimate throughput as well. So instead of just you know, checking really active network stuff and seeing that, which I'm gonna show it at the end of the presentation, we could also do it to just, you know, measure how like, you know, on a router in the LSS network, there's probably a display somewhere that is showing how many megabits per second are in use right now. And we might make that display remotely. It might work. I have to take a look at that. So anyway, let's go to fun graphs now. So this is a graph. We're still measuring using the same methodology remotely. We're using 50-byte packets, and a computer analysis network is running a speed test. You can clearly see the part of the speed test where data is being downloaded, and you can see the part of the speed test where data is being uploaded. So again, really good, really happy about this result. We see different patterns emerge, which means building a pattern database, which is the long-term goal of this research project, is, you know, not out of the question. And it makes sense because of how ISPs configure network devices, that uplink and downlink would behave differently under load. Okay, now to the most important, most interesting slide, the traffic patterns. So afterwards, I did run the test using multiple packet sizes, using the latest toolkit, of course, which produces normal data. And net flow was being recorded on the target network. And I correlated all that together, so we're going to take like 5 minutes trying to go through that. Here we are. So in the graph, we see the latencies on the bottom using dots, and the horizontal lines come from the net flow data. And from net flow data, I took the connections which have a certain amount of packets being sent in the connection. By the way, what I'm not showing here is ICMP part was also logged, of course, in NetFlow. The ICMP that I'm using to measure what's happening on the network. It was 0.10 megabits per second for approximately 6 minutes at 24 packets per second. So approximately 20 times higher resolution than what I had in the first versions, where I was sending 1 packet per second. So, and here we can see stuff, right? Let's start with the leftmost here. So we have the red and the black here. So basically we can see that so there is two-way communication here, this two-way connection, of course, and this IP address belongs to an ISP, a different ISP than I was using and that the target network was using, and it was once again a speed test. The file was being, well, not really speed test, but a large file was being downloaded to the network, and we see the pattern that we know so well from the previous slide right here, right? And we see that all the packet sizes are of course affected. Right? It was downloaded at 92 megabits per second. Now the next part here, at 42 megabits per second from this IP address. This is YouTube's IP address. So 4K videos are being watched on YouTube, and we can clearly see a different pattern emerge here. So there are chunks, there's buffering in the browser. We can see that happening right here. Then the third part here, the green and the orange, is operating system updates being run, and a small part of those updates triggered download from GitHub pages. And the GitHub pages behave really interesting. Probably since Microsoft bought them, they do weird stuff. But we see that even though it's like 40 megabits per second, apparently the way the connection is set up triggers really high increase in latency. for the network at that time. And finally, the fourth connection here on the bottom, 97 megabits per second from the target up to the internet, the same IP address as before, so data is being uploaded for speed test purposes to the online machine over there. So basically that is it. That is what we have right now. There is some stuff to develop. It's sad that I haven't gotten any real programming language to be able to work with this, but Ping works really nicely. I don't know why it works, it just works, and I know you can visualize that as well. So that's it. We have quite some time for questions. If you wanna do some questions, I'm right here. Thank you.
Did you try to take into account the congestion algorithms? Does it even influence the results?
So we are measuring the delta between the nearest uplink router and the target router, and usually there are no fancy algorithms on the target router. So the ISP, the target ISP will apply everything in the same way.
Okay, but you still have congestion, right? I mean, you gotta, as a router, limit your speed somehow.
Yes.
So how do you do it? Is usually drop fast and grow slow.
See,
So-
there doesn't. If I'm understanding your question correctly, there doesn't have to be congestion for this to work. That is proven by the YouTube part here, right? It doesn't. It only takes up about half the bandwidth, and the latency isn't that high, but it's visible.
I'm not really sure, but after 2031, that looks something like a conjunction, but I'm not reading the data properly, probably.
You mean here?
No, right. Yeah, that one.
Oh yes, yeah. But that's the uplink, right. I think this pattern, if you're talking about upload, I think this pattern is being caused by how ISP router is configured.
Thank you.
So you mentioned that you were using a normal router that doesn't have any fancy algorithms. I've seen on many home ISP routers that they have some quality of service type thing that will, I don't know, prioritize voice packets or things like that. So could that impact this data as well? Although I assume all of this is just HTTP, so shouldn't, but I don't know.
I should take a look at that. I would imagine that it will provide even more diverse patterns. If you do quality of service on different stuff, then it will impact the latency even more, I think.
Yeah, just a quick question. Can you tell us what type of connection is on the target or Alice modem? So what is the type of connection from to the ISP? Last mile.
It's 100 base TX, if that's what you're asking.
But it's like it's Ethernet. It's not
Yeah, twisted pair
GPON.
Ethernet. Yeah.
Okay. So there is no like GPON, DOCSIS, DSL.
No. This data presented here today has not been verified against DSL, but that will be fun. Yeah, you know, if anyone wants to do some research remotely, like next week or in 2 weeks, ping me on here, or Kirils.org also has my email address. Yeah, if you have like different kinds of connections, that will be fun. Yeah.
I saw some products for traffic analysis, and I saw that some companies has proprietary algorithms. They can recognize YouTube video and even difference between YouTube stream. And based on that, you can analyze for some specific region what actually user is watching. So they have a software that can recognize it's some video stream, and on that region there is some live stream event, and you can detect even that by this traffic analysis.
So the software you're referring to, does it have to be in the path of the data?
It's working on the traffic analysis. They are taking the data and analyze this data.
Of course, that's really classic. There is a bunch of exploits and different algorithms that you can use to analyze traffic if you actually have the traffic. So the thing we're doing here is we do not have the traffic. We are remote. Oh, I should have mentioned. So this works really well from a different ISP. You don't even have to be on the same ISP as the target. You just do stuff remotely and it just works. And while the microphone's coming to the next question, so yes, there are a bunch of analysis being done, and there are a bunch of tools available for ISPs to analyze data if you have the data. And even if it's encrypted, of course, you can do a lot with it. A lot more than we will ever be able to do remotely.
One question. Considering that, especially if you want to do this between ISPs and you're going to move it to, let's say, a DSL line or a 5G or whatever you're going to use, does it make sense to also extend the algorithm to also monitor your first hop, to also calculate your own congestion, because you might be actually congested as well? So you probably should extend to also monitor your home gateway as well as the ISP's first hop.
I don't believe so, because I am. So let me. How do I get to the picture real quick? I can't get there real quick. I'll get there slowly. So I'll go back to the picture there of the setup, and I believe that I should have added it in the end. Yeah, right. So I believe that whatever is happening with my device or with my router here or here will be cancelled out, because I measure these two nodes and I subtract and I measure them at the same time. So whatever is happening, whatever is impacting me here, should of course cancel out. But your question is interesting. So about 5G and other wireless stuff. So this thing might not work if we have wireless link here, any kind of wireless link, 5G or Wi-Fi. That might be problematic, because then we have. So if you're measuring this delta here, then this has to be stable stuff. We could do some weather monitoring, I guess. Like if there's a radio link, we can see when snow is happening or when it's raining back there. But there's many things you can do with this.
Yeah, you started answering my question. Like, what are the implications of this? Like, what would be the purposes you could use this for, like good or bad?
Well, if there's at least in my country, everyone has had this fear of leaving the oven running at home or the iron running, right? So, and I sometimes have this fear of, shit, did I stop the download, right? So I can just check remotely if my download is still running or not.
So you mentioned the wireless link, and yeah, I do agree that there would probably be too much jitter for that to be valid, but that would also include on your end, right? So
no, the question you're asking is the same as there. So anything that happens on my end is cancelled out, because unless it's a packet switching nightmare where every packet gets routed somewhere differently in the middle, basically I get so whatever is happening impacts both packets.
Not necessarily, because especially with Bash, maybe if this were done somehow more controlled, but if you do it in Bash or something that's not fully controlled timing, even a millisecond or less of difference can have a larger impact on the latency due to just Wi-Fi interference or things like that. So maybe if you control the timing down to microsecond level with like Rust or C.
I am controlling timing to microsecond level in Bash.
Okay, I want to see how then.
Based on the previous screenshot, the picture, it looks like when you measure throughput within an encrypted connection, for example, I see HTTPS port. It's a throughput of your client machine to decrypt the traffic instead of network throughput, actually.
It's it may be true for some cases. I don't think it's the case here, because the data. The data is not that We don't have that much data here. It's more related to the algorithm on the client side that is pulling or pushing the data. So here it is an interesting coincidence, of course. I'm looking at the data here. It is an interesting coincidence here that, yes, HTTPS data shows bigger latencies than HTTP data, but that is because all HTTPS data here, all HTTP data here is downloads or uploads. And the HTTPS data is YouTube, where there is no point, unless you want to pirate the YouTube video, there is no point to really download everything at the same time and waste RAM.
No, buffering within encrypted connection made like it doesn't send more data before you encrypted the already received the portion.
Yes, but for YouTube, I mean, I haven't looked at the algorithms lately there, but I would believe it's not about whether your CPU can decrypt the data, it's about how the buffering is configured, right? If you're watching a 5-hour video, even if your CPU can handle it, YouTube doesn't want you to store 5-hour video in your RAM at the beginning of the video.
Did you try any non-network tuning? For example, a few days ago, the real-time in Linux was merged. So I don't know, at the top of my head, I don't know if it makes a difference, but did you try different tuning of your system, and what makes the difference?
Of the target network?
Target, source, whatever.
So no, the tuning that I tried, I discussed during the presentation. So I was tuning my terrible code and trying to find the right packet sizes for now.
Thank you.
Okay, I think we don't have any other question. So thank you everyone and enjoy the evening.
Thank you.